At the farthest point, Orion will be some 1,000 times farther from Earth than the International Space Station, at over 270,000 miles away. Teams in Mission Control Houston and at Naval Base San Diego will prepare for Orion's return home, and the recovery ship will set sail for the recovery zone in the Pacific Ocean. Orion will exit the distant retrograde orbit with another lunar gravity assist and service module engine firing. Along the way, the trajectory will be adjusted to target the Earth's thin atmosphere at over 250,000 miles away and ensure precision landing in the Pacific Ocean following a direct entry. During the coast home, Orion will maintain the desired tail-to-sun attitude to optimize spacecraft cooling and maximize power production in the deep space environment. Another 4 days return coast home to Earth. As our home planet fills the windows of Orion, an important contribution from our European partners called the service module has done its job. The service module is jettisoned and separates. Following separation, the world's largest heat shield will be oriented into the direction of travel to prepare for entry interface at an altitude of 400,000 feet. At entry interface, Orion will hit the Earth's atmosphere traveling at a speed of 24,500 miles an hour and decelerate at up to 9 times the force of gravity. The heat shield will protect the spacecraft from temperatures half as hot as the surface of the Sun, approaching 5,000 degrees Fahrenheit. Orion will continue to decelerate, pass through the sound barrier, and announce its arrival to the waiting recovery team with a sonic boom. Following peak heating, a protective thermal cover that sits over the parachutes will be jettisoned. This begins a series of parachute deployments. The drogue chute deployment series is designed to stabilize and slow the spacecraft, and in a period of less than 20 minutes, Orion will slow from a speed of Mach 32 to 0 at splashdown. The 3 main parachutes will deploy and slowly unfurl and suspend the 22,000-pound capsule and allow it to gently descend to the surface of the ocean. After 25 and a half days, and a total distance traveled exceeding 1.3 million miles, a precision landing within eyesight of the recovery ship. Following splashdown, Orion will remain powered for a period of time as Navy divers approach in small boats from the waiting recovery ship. After a brief inspection for hazards, the divers will hook up tending lines and a tow line. The capsule will be then towed into the well deck of the recovery ship, and once the capsule clears the stern gate, the gate will be closed, the well deck will be drained, and we will bring our ship home. We invite you to follow along at www.nasa.gov/exploration.
Facility, or PIV, at Space Launch Complex 41, where cranes lifted the 33-meter or 107-foot-long booster onto the Mobile Launch Platform, or MLP. 2 days later, the pre-assembled interstage adapter, so far interstage, in the lower half of the payload fairing was delivered to the bed and lifted atop the Atlas V booster. The stacking of the rocket was completed on May 5th. The X-37B encapsulated
we got another fire. Can you find anybody that could come in and help us?
But we had no visual of which fires were burning where.
We have to learn from this. We can't tolerate this level of damage, this many deaths.
The key factor now is how can we make use of our NASA data?
To see if the fire we're fighting, we used the NASA MODIS satellite system.
Okay, copy that.
To be able to put in instrumentation ahead of a real wildfire is almost impossible to do.
There we go. The X-37B Orbital Test Vehicle is an experimental test platform managed by the Department of the Air Force Rapid Capabilities Office. Let's take a look at this.
One of the basic tenets of NASA was to study the Earth, study the home planet. So fire is an important role player whether it be with the atmosphere or the environment and its effects on vegetation. So fire just becomes a natural subject for the study of Earth processes. NASA data and NASA modeling efforts and NASA science capabilities, which derive from our satellite orbital assets and allow us to basically cover the full spectrum of fire, from predictive analysis, active fire monitoring, to post-fire rehabilitation and recovery.
It was a normal night, and then my phone rang at 12:30, and it woke me up. You could hear the wind howling.
I started getting texts in the middle of the night, people asking me if my parents were okay. About 2 a.m., I get a text from my boyfriend who was out of town, and he said, "Are you okay?"
Environmental dispatch, County Tuna Fire, go ahead.
We see a fire in the distance in the Napa Hills, just north of the city of Sonoma.
We have a report of a tree and house on fire. So I called about 10 minutes ago. There's a house on fire right next to the house we're staying in.
I smelled smoke. Went out on the front porch, and the sky was glowing orange and bright. The wind was blowing like 40 or 50 miles an hour, and the fire was close.
Vegetation fire, City of California, Highway 128 crossing Tubbs Lane.
911 fire emergency. We got another fire.
Okay, I'm sorry, we can't even take the calls anymore.
Can you find anybody that can come in and help us? Anybody, all hands on deck, all hands on deck.
I was the division chief in charge of central operations in the Sonoma Lake Napa unit. One of my responsibilities was the oversight of the 911 dispatch center. As I drove into the command center, I passed numerous fires on my way in. I arrived, and for the next 30 days after that, I never left.
The Tubbs fire basically started late evening between 8:30 and 10 p.m. on a ridge between Napa and Sonoma County, the wine country of Northern California. High winds were blowing from northeast to southwest. We call those Diablo winds. Some of the modeling that was derived from our Landsat data and micro-terrain relief modeling indicated that the winds at the summit were blowing over the ridge at almost 90 miles per hour, with sustained gusts above 70 miles per hour. The fire started from the downed power line or a transformer that was affected. And then with these 90-mile-an-hour winds, there was no way anybody was going to control that fire. When it got into some of the more developed urban communities, such as the Coffee Park area, because of the configuration of the winds blowing through that cityscape and the angular momentum created by the building structures, we created these fire whirls or fire tornadoes, which therefore burn or have speeds of up to 200, 250 miles per hour, burning through the community. So that's even pushing fire even hotter and into this urban environment that's composed of building materials, chemical agents in people's garages. So it wasn't just being sustained by vegetation burning at that point, it was being sustained by structures burning in progression down the fire line.
Our intelligence for the Tubbs fire was all based on the 911 reports we were receiving and the radio reports that we were getting from our fire resources and our law enforcement officers out in the field. But we had no visual of which fires were burning where or the magnitude of the incident. When we started getting reports of houses on fire in Santa Rosa, we couldn't comprehend that that could be the same fire that was burning in Calistoga because of how quickly that fire burned. And if we had had a bird's eye view, some kind of imagery so that we could get a picture of exactly what we had, that would have been a game changer. We're actually using some of the National Guard's manned and unmanned aerial assets so that we can practice the surveillance of our fires.
Testing. Aircraft and gimbal line of sight.
One of the major things that we have them help us with is some of the perimeter mapping and determining the exact location of our fires.
You ask almost anybody what California is known for, and it's either California burritos or wildfires, one or the other. A system we heavily rely on is the MODIS satellite system that is provided by NASA that does hotspot detection on the Earth's surface. And we use that to see in near real time where those hotspots are of that fire that we're fighting.
Okay, we got it.
And then we bring in track data and other layers to basically build that combined picture.
That's it? Okay.
First responders, they want to know which houses have been damaged as quickly as possible, and the smoke may or may not have been cleared. But using radar, we can see where those houses are and where we maybe need to focus our efforts based on how a wavelength might bounce off of the surface. We can actually see through smoke and clouds. We can see things like vegetation structure or building structures.
We're going to support the North Ops, South Ops for fire season, which we're now pretty much defining like April to New Year's Day of next year.
We'll have a pretty good idea what the fire's doing early on, like on the campfire, where it starts so quickly and you see what's in front of you, but you have no idea what it's doing anywhere else. Like, that's where we could come in and provide a much better picture. And so I have NASA MODIS and VIIRS stuff, which we always use on Google Earth. You can kind of see the streets here. This is a neighborhood totally burned down. And CAL FIRE, they weren't used to being able to see through the smoke. The perimeter was right here, and they see right here there's a raging fire. They know the fire is now way out there.
Remote sensing is really important for the mapping of those incidents, and then also to help us figure out where those hot spots are.
We're outside of our 30-mile limit. So we've got a fire out of our right wing towards the north.
CAL FIRE, go ahead and report it.
Prior to having the capability, we would draw by hand basically where the fire perimeter approximately was. Now, with the MODIS data being pulled in, we're able to see irrefutably where that fire was last known to be.
So look, here's what it looks like. So here's
remote sensing application has been a game changer in allowing us to see real time where our fire is. So our operations folks are able to make tactical decisions real time based on where our fire truly is.
What is a CubeSat? CubeSats are very small spacecraft that orbit Earth. As you might guess, a CubeSat is shaped like a cube, about 4 inches wide, long, and deep. That's called 1 unit, or 1U. Small enough to hold in your hand, and very light, around 3 pounds. And like building blocks, units can be combined to make bigger CubeSats by stacking them into 2, 3, or even 6 units. Once in space, CubeSats can open up all kinds of tools: solar panels for power, communications antennas, telescopes, and more. CubeSats are great because they let schools, universities, and other teams launch their very own missions, and who knows what they'll discover. CubeSats are also made from standard, low-cost parts that are easy to get and tested for launch safety. Some NASA launches carry spacecraft that don't take up all the space on their rockets, which leaves plenty of room for tiny CubeSats. Build a CubeSat, catch a rocket ride, and you become a space explorer.
Our primary objective is structure protection and just trying to stop the spread of the fire into the adjacent houses.
Looks like hundreds of homes possibly.
Hundreds of homes. We just got here this morning. I can't even give you a number.
There was a second phase where when the winds died down, we continued to have a more typical fire event, which was driven largely by the fuel loading in the landscape. As a result of the work that we did in collaboration with NASA, we were able to really separate those two events because we had really good data about wind levels and the time.
Our plants have been affected by years of drought. It means that we have years of dead fuel buildup in the state. It's called fuel load, and it's basically how much plant material there is within a specific area. And as that continues and continues to increase the amount of fuel loading, our fires burn hotter and more intense and quicker.
It's in the relationship between topography, fuels, and climate that drive a fire across the landscape. The heat generated from the fire, especially in steep terrain, is what's propelling these fires forward. And then you add to it a growing wildland-urban interface, we are seeing just more impactful fire events and hence the increase in megafires.
35 seconds into flight. Altitude now just under 1 mile.
The key factor now is how can we make use of our NASA data in the recovery operations.
We need to understand why some people lost their homes and other people didn't, why some watersheds burned. We need to understand the intensity and the damage done by the fire.
Seeing now.
So this is the post-fire imagery?
Matching up with what we're seeing now, a lot of this area within our view was burned.
So what was the fire direction? We're looking at it here. I mean, kind of from this direction, burned down. And
the fire started down in the canyon.
Okay.
And it actually burned to the east.
Right, okay.
And then the wind shifted and this part of the canyon burned in the topography-driven fire.
Okay.
Later on.
Okay.
Yeah.
after the fire burned. We needed imagery right away to understand the damage. Because now, several years after the fire, a year and a half, there's a lot of regeneration. If you have ladder fuels, that's the fuels from the ground up to the canopy. If the ladder fuels are dense, the fire's going to burn hotter, you're going to have more damage. And with LiDAR imagery, now we understand that.
The way that LiDAR works is it will tell you the distance from the sensor of each point return. So when you send out a pulse and you get it back, you know exactly the distance that it traveled. And if we did that with billions of points, we can actually recreate three-dimensionally all of the structures in a space. We can construct the vegetation, we can even construct to the leaves on the trees.
A fire that burns through an ecosystem will start out as a ground-based fire primarily, burn up through vegetation communities and get into the crowns of trees. That's called ladder fuel development, which leads to a greater chance of very high severe wildfire.
We can now map the ladder fuels and where they occur across the landscape. Then we can compare where they occur next to homes or hospitals or roads. And with those things together, we can prioritize treatments for fuels. So we're going out of this study really well armed to be able to manage fire risk across the landscape.
After the fire, when I drove through the Coffee Park neighborhood, which was a half a mile from my house, the thing that struck me was how much it looked like images of Hiroshima and Nagasaki during World War II. All that were left were standing chimneys, brick chimneys. Everything else was totally consumed, burned to the ground.
We've been using wildfire as a tool for millennia. We've been using it for cooking, to grow crops and nutrient cycling. So we've had this relationship where fire is a tool, but at the same time, it's also a natural disaster, right? We don't think of hurricanes as tools.
I had revelation that prescribed fire was an important part of restoring ecosystem management over about the last 10 or so years, and we need to make it a consistent part of our management of our resources. Introducing prescribed fire into that ecosystem allows us to remove some of those underlying ladder fuel components and allows that forest floor to kind of open up and not have the propensity to burn in dramatic wildfire style.
This is part of a very large project that's called the Fire and Smoke Model Evaluation Experiment, and it's as close to a wildfire as you can get. The objective is to collect a suite of data to both evaluate and advance our fire and smoke models. To be able to put in instrumentation ahead of a real wildfire is very dangerous and almost impossible to do.
NASA founded our previous project that actually allowed us to build, this prototype with the fire model. It's focused not just on the prescribed burns, but also on wildland fire. We were able to get, the new forecast run just, before the briefing, and just right after the briefing, we get the first results. So we had an idea about the wind speed, rain.
Winds aloft are going to be start to crank this afternoon, so there's going to be a sweet spot early this afternoon.
So what time are they thinking of igniting?
So this part of the unit over here, we're looking at around 1300, 1400, letting the sun get on it. This is our one concern area where we have continuous fuels. We're going to send the hot shots that are rolling out of here right now.
We see in all the valley over there. I mean, we should be in a good spot to set up our truck in the LiDAR. There's gonna be a more intense burn, but also in the plume should be going like this direction, so we will be able to really have a good angle.
Right here, and then transition is gonna be the
I think we have so much better chance, for the fire to take off and kind of, start moving, freely after the ignition. So from that standpoint, I mean, it's gonna be, really interesting.
Air temperature, 65.4.
Attention on the crew net, attention on the crew net. The helicopter is airborne and they are igniting test fires at this time.
So topographically of where they're going to go push and drop another barrel of gel is in a slot canyon right back over there. And so it should follow this, maybe be over it, but we'll be underneath and be able to watch it just go right over us. Cool. So.
X-37B Orbital Test Vehicle. Can you tell us a little bit about the history?
A lot of smoke, so I think we'll get something out of it.
We had to move back up the hill here to clean air while the column folded over on our location there.
So I'm super happy. I kind of believe that our forecast it was really spot on in terms of how strong the winds are over this region. The same in terms of the plume location. I mean, you see that we are actually really close to the plume, and that's what we wanted. 5 years ago, when we were talking about real-time coupled fire atmosphere forecasting, and people were saying that that's impossible. 5 years later, I mean, we have completely different computational power, to execute, those forecasts. I mean, we can really do that.
That's really the takeaway message for this whole program, is that he was able to initiate his model today and yesterday and get a forecast that matches what we're seeing.
So I'm super happy that NASA had a faith, in this whole idea. It's great, to see that, running, working, and I hope that, pretty soon, other people will be using that, and it will be very helpful in designing prescribed burns, but also, in terms of fighting wildland fires.
This is the home site right here. This is the garage right here, and then you can see the patio in the back. The fire was coming from the northeast. Once it hit that stand at Douglas Fir.
Up on that ridge out there.
Yeah.
500 yards out or something.
Then it was all over.
We started seeing the first MODIS fire detects from our MODIS satellite and VIIRS satellite, but primarily MODIS at the nighttime overpass a little bit after that. Yeah. It'd be great if we can get some of that information to earlier detection capabilities to mobilize resources to evacuate people.
In a widespread disaster like this, people appreciate each other in a different way. They chose to come together to help each other instead of trying to everybody solo it. And doing so made us all stronger as a community.
With climate changes, fuel loading changes, we are seeing an earlier start to fire season, and we are definitely seeing a longer length of fire season.
We have to learn from this. We can't tolerate this level of damage, this many deaths. Our small study we did with NASA is turning into really important tools for other communities throughout Northern California.
Our last mission was 780 days, and that's just a lot longer than a shuttle could stay aloft.
What have you learned in the past 5 missions that could be applied to the industry moving forward?
Hello and welcome to NASA Science Live. Today we're discussing important science around Earth's icy regions and how it can impact those living in warmer regions around our planet. You might have heard in the news that enough ice has melted from Antarctica and Greenland to rise sea levels about ½ an inch over the past 16 years. We have the scientists behind that NASA study to talk to us more about what we've learned and what it means for our planet. We'll also take you to the coast of Virginia to see the real-world impacts of Earth's melting ice. Before we get started, let's take a step back and learn about the cryosphere. That's the frozen water parts on Earth's system.
Here at the end of the Earth, it still feels like a place for raw exploration and adventure. It's vast in all directions and ground zero for some of the biggest questions we have about the climate. But when we decided to make a show about the frozen places on Earth, we knew there would be one hurdle we would need to jump over first.
What is the cryosphere?
The what?
Ooh.
I have no idea.
While I'm aware of the cryosphere, I don't actually know what it is.
It has something to do with ice.
All right, that's all I got.
How do you get people acquainted with the cryosphere when most of us don't even know what it is?
Hey, so here we are in Washington, D.C., standing on the roof of NASA headquarters. That's the Capitol building right behind me. And what headquarters does is kind of serve as the focal point to connect the dots. The cryosphere is everything from the snow that falls by your house to the icy reaches of the Himalayas, to the big ice sheets of Antarctica all the way at the South Pole, and also the frozen ground of the Arctic, and even some of that frozen ground that's currently under the ocean.
If you had to break it down, you'd have a mix of sea ice, snow cover, permafrost, ice sheets, and glaciers.
Right now, our best predictions are that sea levels will rise anywhere from 1 to 3 feet within the next 100 years. 3 feet of sea level rise has the potential to displace about 100 million people, which is a lot of people that need to find new homes.
Our current reality places us at a near tipping point, and the cryosphere is playing a huge part in that delicate balance.
So one of the things people don't know about NASA is that we study the Earth, and we've been doing that since NASA's inception back in the 1950s. And we study the frozen part of the Earth in a variety of ways.
Missions like SNOW-X, Airborne Snow Observatory, Oceans Melting Greenland, Operation Icebridge, Arctic Boreal Vulnerability Experiment, and countless other labs and individual researchers stand at the forefront of monitoring the cryosphere. We're taking you with us as we follow NASA explorers on their journey to the frozen ends of the Earth as they study our rapidly changing world from satellites, planes, and boots on the ground.
Wow, so it sounds like the cryosphere is a place we all depend on, but many of us will never go to. I'm joined today by Alex Gardner, NASA glaciologist. Alex, can you tell us more about why NASA studies Earth's ice?
Yeah, absolutely. NASA studies Earth's ice because it's incredibly important for the rest of the Earth system. The poles cover a large region of the Earth, and they interact with the Earth system in ways that cause large global changes. The melting of the ice sheets are responsible for changes in sea level rise. The formation of sea ice drives the thermal haline circulation, or the circulation of the ocean. Changes in snow cover year to year cause large changes in the Earth's energy budget. And so if we want to understand the Earth, we need to understand the poles.
So how does NASA study Earth's icy regions?
Yeah, great question. There's a lot of different ways that NASA studies the polar regions. And NASA's really well equipped to do this because these are very harsh environments that are dark for up to 6 months of the year. And so NASA has a suite of satellites and airborne missions that are designed to study the polar regions. We have a satellite that launched in 2018, ICESat-2. That's a very advanced laser altimeter that counts individual photons that bounce off of the Earth to measure height changes. We have another satellite that launched in 2018, the GRACE follow-on mission. And this is a fascinating mission that's able to actually measure subtle changes in the Earth's gravity. So as the ice sheets grow or shrink, we can actually see gravity change in response to those changes. And we also have the airborne missions. So we have a mission called the Oceans Melting Greenland that surveys the periphery of the Greenland ice sheet to measure changes in oceans and see how that's impacting the ice sheet.
What are some of the discoveries that your colleagues have been making about these regions?
Yeah, so it wasn't very long ago, only a few decades ago, we assumed that the ice sheets would respond fairly slowly to changes in climate. And what we've discovered over the last few decades is that's far from the truth. There are all these really interesting feedbacks that occur that cause the ice sheets to respond much more rapidly than we had anticipated. So the oceans are able to eat away at the edge of the ice sheets very quickly, which causes the ice to flow more rapidly into the ocean. We've discovered that water from the surface can easily reach the bed of the glacier, raising the pressure at the bed of the glacier and reducing the friction that causes it that resists the flow into the ocean. And in some places, we've discovered that the geometry of the bed of the glacier can cause glaciers to retreat irreversibly once they start to retreat. And so there's these large one-way feedbacks in some places that can cause rapid changes in sea level rise.
It is such an interesting region. We've got some questions from social media. So we have on Twitter, Rut13 asks, what kind of information can we get from ice, and how can that information be useful to us?
Yeah, so there's lots of different